These are the notes for the fourth page of your notes. We've done just done the ships in the fog problem, and now we're going to look at the general parametric equations for motions. Notice that when we break our parametric equations into x as a function of t and y as a function of t, and we're dealing with motion, we always follow this form. X of t is some initial x position, the velocity in the x direction times time. Y of t is the initial y position, velocity in the y direction times time, plus 1/2 gt squared, which is the acceleration due to gravity if gravity is involved. In the ships problem, the ships in the fog problem, gravity is not involved. The ships are not being thrown in the air, launched, or they're just kind of sailing along the water, so we don't use this term. But if we're doing projectile motion, throwing something in the air, throwing a ball, launching a rocket, that kind of thing, we would include this term. Notice that x sub 0 and y sub 0 tell us the position of the moving object, or I'm sorry, x sub t and y sub t tell us the position of the moving object at time t. So a couple ways that can be written, we'll probably be using this notation with our subscript representing the little 0 representing our initial starting position, velocity in the x direction, velocity in the y direction. If you have been in physics, you've seen a very similar equation, a little more complicated subscripts where d stood for displacement in the x direction, initial displacement in the x direction, initial velocity in the x direction, etc. Our initial x and y position is when t equals 0, which is why they have the little subscript 0 by it. Velocity is in units of distance divided by units of time. Velocity is a vector quantity, so velocities can be negative in the x and y direction. Initial velocity, however, will be, if it's just velocity in the diagonal direction, which we'll talk about in a minute, that would be positive. Now, if we look at these equations as applied to the Helsinki ship that we looked at, notice that here x sub 0 is 900. That is our initial x position. And the -3 represents our initial velocity in the x direction, our velocity in the x direction, which was -3 millimeters per minute velocity in the x direction. And then, of course, t is time in minutes in this case. When we look at our y equation, our y sub 0 is equal to 0. There was no initial x velocity or x displacement. And then 2 millimeters per minute was our velocity in the y direction. And once again, no gravity involved here. Now, we were given our x and y positions in terms of +2, we were given that we went 3 in one direction, 2 in another, 4 millimeters in one direction, 1 in another every minute. So we were given our velocities just by giving our x and y velocities. But what if we were given our initial information a little differently? So we're going to do the two ships problem again, but with different starting information. And I actually tried to make it similar, but it's not exactly alike. But they both do have their same initial starting positions. Andy Adaria still at 900, 0. Helsinki still at 0, 100. But now the way they're traveling is described differently. The Andy Adaria travels northwest at an angle of 134 degrees at a rate of 3.7 millimeters per minute. So if I think, well, this is straight north, this is 90 degrees, then, and this is straight west, 135 degrees is almost exactly in the middle. 134 degrees is almost. 135 would be halfway between 90 and 180, but this would be 134 degrees. And then our initial velocity is 3.7 millimeters per minute. And notice that isn't velocity in the x direction or velocity in the y direction. That is velocity along the path that the ship is traveling. When I do the Helsinki, I have a similar information, only I have a 24-degree angle now, which is a very small angle, just up to the right a little bit in north. This is 24 degrees, and we're told this is 4.2 millimeters per minute. So in this case, the speed's being given directly to us, and the direction is determined by the angle. I did want to point out that, and I might have mentioned it in the previous slide, but I'm not sure, that often, I'm just going to do this kind of as a little side note, that often when you're dealing with navigation, that the way the angles, that's not west, that's south, the way the angles are actually named is not the traditional way we've been doing it in math. In navigation, usually north is 0 degrees, east is 90, south is 180, and west is 270. So I'm not going to switch things up on you. We're going to do the same kind of angles we have been doing. That would be bearing. And actually bearing's worth studying, but I'm not going to do that right now. Just letting you know, though, that probably you would be using 0 as north if you were really doing a navigation problem. Okay, equations. How do we handle it when we're given a theta, an angle, and a speed in the direction of the path instead of the speed in the x and y directions? Well, the same thing we've been handling it all year long. We draw a right triangle. Some of you are probably already ahead of me on this. These are vectors. These are velocity vectors. We talked about vectors. Velocity vectors add like this. And this is just a right triangle. This is our velocity, and this is theta. So I can say then that cosine of theta would be Vx over V. So I can say that velocity in the x direction is going to be the velocity times cosine of theta. And I know that sine of theta is Vy over V, so rearranging that equation, I get the velocity in the y direction is velocity times sine of theta. So now I can use that information to help write the equation here. So equations for Andy-Daria. X of t is the initial x position, which is 0, plus the velocity in the x direction, which would be 4.2 cosine 24, and then t. Make sure the t goes outside of the cosine function. Y of t then would be the 100 plus 4.t sine of 24 degrees t. Now, equations for the Helsinki. X of t is equal to initial position 900. And now we run into a little issue here. When we did this right triangle, it was a pretty basic right triangle. We have 24 degrees here, we have Vx, Vy, and 4.2. So pretty easy to determine how we're going to handle that right triangle. Here, though, the right triangle is actually over in quadrant 2 here. My Vx is to the left here, my Vy is up, and there's an angle in here of 46 degrees. So which angle do I use, the 46 degrees or the 134 degrees? Well, the answer is the 134 degrees is the angle that is in the formula. However, with care, you can use the 46 degrees also. So let me just show you what that would look like on the calculator. Okay, I typed in both equations here, 4.2 cosine of 24, 4.2 sine of 24. So I could get the decimal forms of those directions as well. However, when I type in 3.7 cosine of 134 and 3.7 cosine of 46, the two different angles, notice I get opposite values. So I'm going to drag this over into my thing here, my notes, and I want to take a look at this here. Delete that one. So when I am writing this, I have to be careful. I have to look at the fact that I have, and the x direction is a negative direction. So I can, if I use the 134, the 134 degrees is in quadrant 2, so using the 134 automatically makes the x direction negative and the y direction positive. I don't have the y calculated for this particular one. I probably should have done that. Matter of fact, I think I'm going to pause and do that right now. Okay, so what have we got here? Notice cosine and sine of 24 are both positive, as we would expect. Cosine of 134 is negative, and sine of 134 is positive. That matches what we would expect to see. If we use 46, Oh, that was supposed to be a 46, not a 24 there. Darn it. Obviously not editing these tapes much, as you notice. Okay, I've got the correct answers now. So sine of 134 and sine of 46 are the same number because sine is positive in both quadrants 1 and 4. So that's not going to be a problem. However, if you decided to use 46, you would have to remember to make the cosine value negative. So here's what I would suggest. This is the way I would suggest to write it. 900 plus 3.7 cosine of 134 degrees t, and y of t is equal to 900 plus 3.7 cosine of, sine of 134t. Doing it this way, because of the 134 being in quadrant 2, it automatically makes your x component negative. Now, if you really feel a lot more comfortable using sine and cosine within the right triangle, you say x of t is equal to 900. Oh, sorry, this is not 900. There is no y starting value. That should be 0 here. 0 plus, which of course you don't have to type in. Some of you are crying half point desperately at this point, I know. I would have to say 900 minus 3.7 cosine of 46 degrees. If I chose to do that, I would have to have the minus in here. And then y of t would be 3.7 sine of 46. And I would not have a negative sign in front of the sine. So it requires you to remember some things if you do it with the 46. Somebody just came to the door, another interruption. Oh well, I'm back. If I put this in decimal form, then I could, so a third way of writing it would be x of t is equal to 900, let's see, cosine of 1 minus 2.57t, and y of t is equal to 2.66t. So there's a lot of different ways to write it. But you have to make sure that the answer is reasonable. So for those of you who may find that putting it in decimal form makes more sense to you, that might be a good option if the angles themselves leave you kind of hanging. But most importantly is to make a picture. Make a picture. Draw the situation. If you draw it and you look at it and your work needs to match what you see in the picture, that will catch so many more mistakes if you do that. So in general, we can say then that given v and theta, that we could write our equations as x of t is equal to the initial x value plus v cosine theta times t, and y of t is equal to the y starting value, the initial y value, plus v sine theta times t, plus 1/2 gt squared if necessary. And remember, that is our constant due to gravity. So that is showing you that you can have the same problem with different starting information and how to work with both types. Then the next video is going to talk about something that actually involves gravity.